In this lecture we talk about homology of the total complex. So I will just talk about the general idea and the overall picture. The details and the proofs can be found on page 628 of this book, Introduction to Homological Algebra by Joseph Rotman, and I'm using the second edition. So say M is a first quadrant pi complex. So we have already constructed this as a total complex. And if you have this M, then you can use a vertical filtration and a horizontal filtration. So the first spectral sequence you form is using the vertical filtration. So filtration by column, and this is what we denote by the spectral sequence, which is obtained by just using the vertical filtration. So one spectral sequence, and from this total complex or bicomplex you can again form a second spectral sequence. So the second spectral sequence you can get by using filtration by rows. So this is horizontal filtration. So this number 2 denotes the horizontal filtration. So we have two spectral sequences. So there is a theorem which says that both these spectral sequences converge to the homology of the total complex. So the homology of the total complex is given on page infinity. So on page infinity, on the anti-diagonal lie the homology groups. So you take the direct sum of these. So you take the direct sum of the elements lying on the anti-diagonal. You get Hn of our total complex. Now this Hn is a graded ring because it's the direct sum of all these elements lying on the entire diagonal. So note that the graded rings for both the sequences, so both the spectral sequence 1 and spectral sequence 2 on the page infinity, so both these graded rings are the same because both the graded rings are homology of the total complex. So that is collection of the terms lying on the anti-diagonal are equal. But the infinity pages might be different. So it might be the case that the spectral sequence obtained by using the vertical filtration, so this is the vertical filtration, and the spectral sequence obtained by the horizontal filtration, their terms might be different. So this term, so say for example this is for vertical and you have another for horizontal. So this is for horizontal, so this might not agree with this, but the direct sum will agree. So these terms might be jumbled up. So they might be jumbled up. That is because both vertical and horizontal filtrations, they will induce a different kind of filtration on the homology group. But the direct sum would be the same. So this, take the direct sum here, you will again get Hn of the total complex. Take direct sum here, you will again get the Hn of the total complex. But you cannot guarantee that these individual terms are the same. So these might not be the same. So they might be in some sense jumbled up. So the easiest application or the most used application is that when either row or column is exact. So if the row or column is exact, then you already know that there are no homology groups, and you know the page infinity just consists of zeros. Now if this just consists of zeros, then this can lead to discovery of some non-trivial relations. So we have already used this remark number 1 in proving the snake lemma. So number 2 is for row filtration. So you know that in the row filtration the arrows are going like this, but we want to fit this to page 0, so you have to transpose these arrows. So you have to again rewrite the entire filtration so that the arrows go like this. So this is for the second. For the first E, it does not matter because first E the arrows are anyway going like this, so you have the page 0. For the second you have to transpose it. So for the row filtration we have to transpose the rows so that you can make into a column, and therefore you can fit into page 0. So this will become more clear as we discuss another example where we will use the second remark. So in the next lecture we will make an example on balancing Tor, and in which we will use this remark number 2.